Welcome to Derectronic, where we experiment, learn, and build with electronics. Today, we will be taking a closer look at how a bipolar junction transistor, or a BJT, can operate or operates like an electronic switch. As most of you might know, a switch has two states in general, an on state and an off state. To understand how a bipolar junction transistor or a BJT can have an on state and an off state, we need to study two of its operating regions or states, and they are as follows: its cutoff state and its saturation state. Now, when is a BJT or a bipolar junction transistor in cutoff? The diagram on the left illustrates that. To properly bias a BJT, we need two power sources connected to it. One is to be connected on the base, and the other one is to be connected on the collector. Resistors RB and RC serves as limiting resistors for the base and the collector respectively. The emitter, on the other hand, needs to be grounded. Now, a transistor is in cutoff, or a BJT is in cutoff, if the base current is equal to 0. When the base current is 0, the collector current is also 0. And when that happens, the base emitter or base emitter and the base collector junction are both reverse bias. When this happens, the transistor is similar to an open switch. Or we can also say that when the base current is 0, the transistor is off or on its off state. Now, when is the transistor now in its on state? Now, let's take a look at now the saturation region of a transistor or a BJT. A transistor is in its saturation state when the following things happen, and it's illustrated here on the diagram on the right. Here you can see that we have a base voltage now applied to the transistor. And if that base voltage is large enough to produce a base current that will put the collector current in saturation, the transistor is acting like a closed switch. Now, what does that saturation mean? Typical operation of transistors would be as follows. A base voltage produces a base current, and this base current gets amplified to a much larger collector current. That if the base current goes up, the collector current also goes up by a factor equal to the amplification factor of the transistor, which depends on the type of the transistor. Now, saturation happens when the base current reaches a certain value that if I still increase it, this collector current is not increasing anymore. At that state, we can say that the transistor or the BJT is already saturated or is operating at its saturation region. And as I mentioned earlier, when the transistor is in saturation, it's acting like a closed switch. Or we can also say that when a transistor is in its saturation state, the transistor is on. This animated GIF, courtesy of HomemadeCircuitsProjects.com, illustrates the switching operation of a BJT or a bipolar junction transistor. Here we have an external voltage source connected to the base resistor, and in between them, in the branch between the base resistor and the external voltage source, you have a push button switch. On the collector, connected to a separate supply voltage is a load, here, the bulb, and the emitter is grounded. Now, when the push button between the base resistor and the external voltage source is pressed, this branch between them closes. And when it's not pressed, the branch between the base resistor and the external voltage source opens up. So when the push button switch is pressed, current flows to the base. When the push button switch is not pressed, The branch is open, so there will be no base current. As you can see from this animated GIF, when the push button is not pressed, the load on the collector is off. Why? Because there will be no base current running through the transistor. So base current is 0, therefore collector current will also be 0, and that bulb will be off. Now, when the push button switch is pressed, now the current produced by the external voltage source will now flow to the base resistor. And when that happens, the base resistor or the base current flowing through the base resistor will now be amplified by the BJT, producing a larger collector current. Now, that collector current, if large enough, will turn on the bulb. So it might be interesting to note here that the transistor does not have to be in saturation to turn on this bulb. All this bulb needs is a large enough current, collector current, that is amplified from the base current to turn it on. However, when the push button switch here is not pressed and the transistor or the BJT here opens up or is in its cutoff state, this particular bulb for sure will be switched off. The BJT switching circuit we will be doing in this video is shown here. First off, we will be utilizing a BC547 NPN transistor, wherein you have the collector here, its base, and its emitter. As you can see from this diagram, we will be utilizing two different sources. First is the function generator here, connected to the base, and the second power source is a 5-volt DC supply connected to the collector. Now, similar to the biasing circuit we saw earlier, the emitter of our BC547 will be grounded. The collector, on the other hand, is directly connected to an LED, a red LED, connected to the cathode of the red LED. The anode of that red LED will be connected to a 470 ohm resistor, the limiting resistor on the collector. And that resistor is connected to the power source, the 5-volt DC supply source. Now, on the base, we have a limiting resistor, R1 here, 220 kilo ohms, and that resistor is the one connected to the function generator. Both function generator and DC power supply will be connected to a common ground where the emitter is also connected. Now, the function generator will be set to generate or output a square wave, alternating square wave, with a frequency of 1 Hz and an amplitude of 10 volts peak to peak. And as for the BC547 is concerned, since we know the part number or the model number of the transistor already, shown here on the right side of the slide is the pin configuration of the BC547. Just like in the previous video, with the front face or the flat face of the transistor facing you, we numbered the pins as follows. The leftmost pin is pin number 1, the middle pin is pin number 2, and the rightmost pin is pin number 3. And for the BC547, the pin out diagram is as follows. Pin 1 is the collector, pin 2 is the base, and pin 3 is the emitter. What I have here is the BC547 NPN transistor. As you can see here, it has 3 pins with the flat head facing you. Now, before we start constructing the BJT switching circuit, let us first verify the pin configuration mentioned earlier in the video using this component tester, the Finersi LCR P1. This is the same component tester I used in my Zener diode video. Let's connect it here. I'm going to connect the transistor here. You see the number there, 1, 2, and 3 on this side of the top, with the flat face facing us or facing towards us. Let's do that now. There. See the flat face facing us, okay? Pin 1, 2, 3. So what does that mean, okay? Pin 1 would be the one on the left. Pin 2 would be the middle pin, and pin 3 would be the one on the right. Let's test this one out. Let's verify the pin configuration first. Okay, let's test it now. There. See the test, okay? Okay, it's an NPN transistor, according here. And the pin configuration are as follows, okay? Pin 2 is the base. Pin 1 is the collector. And pin 3 is the emitter. It's mentioned there. So, 1 collector, 2 base, and 3 emitter. We will again use this COM3 Lab protoboard to construct our BJT switching circuit. I've already inserted the bipolar junction transistor here on the board, the BC547, with the flat face facing away from me in that direction. A closer look at that shown here. As you can see here, the flat face is facing away from me. Now, if you take a look at now the legs here, the side, okay, if the front face or the flat face of the transistor is facing away from us, that means the left leg here is actually the emitter, the middle leg is still the base, and the right leg is the collector. Now, let us now connect the other components needed in this circuit. First off, let's connect the ones needed on the collector side here. Now, on the collector, if you could remember the schematic diagram shown earlier, we first need to connect an LED, a red one. Now, polarity is important with LEDs, so we need to know where the cathode and the anode is. Now, the cathode of the LED is a shorter leg, which means this leg, the shorter one, is the cathode, and the longer leg here is the anode. Now, connected to the collector is the cathode side. So I'm going to connect this shorter leg, the cathode, directly to the collector. Like so. There. Okay, so cathode connected to the collector. Now, the anode of that LED is to be connected to a 470 ohm resistor. I have it here. 470 ohms. Now, how do I know this is a 470 ohm resistor? Again, color code. I advise you to take a look at the video I created for resistor color codes to have a better idea on how to determine the value of a resistor based on the colors shown on its body. It's a 470 ohm resistor. Now, what I will do is this, okay? The 470 ohm resistor, one leg is connected on the cathode, and the other leg, if you could remember, is connected directly to the 5-volt source. So what I'm going to do is this, okay? I'm going to connect the resistor, one leg to the cathode here, and the other leg I'm going to connect to a power rail here at the top. I'm going to use the red power rail for that purpose. Like that. There. Okay, so this leg here is connected to the anode of the LED. And the other leg here is connected to the power rail. So on that power rail, later on, I will connect the positive terminal of our 5-volt source. Later on. Okay, now, the emitter side, let's take the emitter side now. Here is grounded. Let's do that now. So the emitter here, I'll connect to ground. So what I'll use for ground for the meantime, again, since I'm close to the top power rail, I'm going to use the blue side of that top power rail for my ground. Connect it there on the blue side. There. She said there. Top power rail. Okay, now, the base is connected to a 220 kilo ohm resistor. I have that here. 220 kilo ohms. How do I know again? Again, color code. Check the colors on the body. Okay. Now, the 220 kilo ohm resistor is connected. One leg is connected to the base, and the other leg will be connected to the positive terminal of our function generator. Okay. Now, for the meantime, let me just connect the one of the leg to the base, and I'll connect the other leg to a free pin somewhere down. Let's do that now. So, one leg to the base, there, and the free pin somewhere down. Push it a little, there. Okay, so this leg of the 220 kilo ohm resistor is connected to the base, and the other leg is connected to a free pin. Now, expect this one of these pin here's below. I'll connect this one to the out pin or the output pin of our function generator. Yeah. Now, let's connect now the power sources, starting with the 5-volt supply. Now, as I said earlier, the 5-volt supply of our power source actually will be coming here. Okay, and the ground of that 5-volt supply will be coming here. So we need to connect power cables coming from these pins. So I could use a red pin for the 5-volt source here, and I'll connect it to the top power rail, red side, where this 470 ohm resistor is connected. Like that. Okay, now, the ground of the 5-volt source, I will connect also on the top power rail. This time around, I'll connect it on the blue side of the top power rail. Somewhere here. There. Blue side of the top power rail. Give you a closer look. Give you a closer look at that. See. There. Closer look at that. Okay. Now, as for the function generator, the power cables will have to be connected on this side. Here. Function generator. See there. Function generator. So the one power cable will come from here, the out pin, that's your positive terminal, and the ground will be coming here from this pin. Now, let's have two power cables now. What I will do, I will connect the red power cable. Connect a red power cable here at the out pin, and a black power cable on the ground here. What will happen is this, okay? Now, let me start with the red first, the positive terminal of our function generator. The positive terminal of our function generator would need to be connected to the leg of this resistor, the 220 kilo ohm resistor. So what I'll do first, let me first connect a jumper wire from these pins going to the power rail down. I'm going to use this time around the red side of this power rail, the bottom power rail. So I will need one more jumper cable. I'll connect it here. Same pins where this leg of the 220 kilo ohm resistor is located, and I'm going to connect it to the bottom power rail. I'll use this one. I'll use the red side. Here. See right there. Maybe just a closer look at that so that you can see. Here's a closer look. There. Okay, connected to the red side of the power rail. Now, the function generator now, the red side of the function generator, I need to connect it, or the red cable of the function generator, I need to connect it to that same line. There. And the ground of the function generator, this one, will have to be connected to the same ground where, or to the same line where the ground of the 5-volt source is connected. Common. So by common connection, it's the one there at the top. There. Now, I could actually switch on the circuit right now because the circuit is complete. Now, what will happen if I switch on the circuit? Let's switch. Before I switch it on, okay, I need to set first the function generator to output the square wave, and frequency, I'll need to set it to 1 hertz, and also the voltage peak to peak, or the amplitude needs to be set to 10. I could actually do that directly here, from here. Okay, you could also do it from the companion software, Com3 Lab, if you wish to do so. Okay, now I'd rather do it on the companion software later on, and just show you what happens when I switch on this board later on. Now, for the oscilloscope connection, what do we do with that one? The oscilloscope connection will be connected here at the top. Again, I'm going to use Y1, Y2, and COM. I'm going to use all three here at the top. So Y1 will be connected to the input, Y2 will be connected to the output, and COM will be connected to the common terminal, okay, of our circuit. Now, let's do that one by one. Y1 first, here, connected to the input. Our input is the function generator line, this one, the out cable. So I'm going to connect this Y1 cable coming from the oscilloscope to the same line where the out pin or the out cable of our function generator is connected. Red line of the lower power rail, the bottom power rail, same line. Now, for Y2, I'm going to use Y2 for the output here. Y2 is the output. Now, output here is that red LED. It's our output. So we're going to use the red LED as the output. So the Y2 cable, this one, will have to be connected to that red LED. Closer look of that one. I have to connect it there on that red LED. Show you. Y2, huh? Okay. Connect it here. Between the red LED and the resistor for the output. There. So between the cathode, same line as the cathode and one of the legs of that resistor. Okay, now, the common, this one, of our oscilloscope will have to be connected on the same line where the ground of both the function generator, this one, and the 5-volt power source is connected. So let me just connect it there now. Here. Same line. There. That will be the blue side of the top power rail. Once that is completed, we've done that, our connection is more or less complete with the oscilloscope included. Once the board is switched on, which is done through the switch here at the top, to turn on the COM3 lab board, and the power source, the 5-volt power source, will need to be switched on from here. This is what you're going to see. You will see the red LED blinking on intervals of 1 second per blink. Now, the intervals there of the red LED blinking can actually be set to a higher value, which means it will blink faster if we change the value of the frequency, as you might know. Now, so knowing this, let us now go to the COM3 Lab companion software to check out the input and output waveforms. Let us now go to the COM3 Lab companion software, where I've already set the function generator to output a square wave and its frequency to 1 Hz and amplitude to 10 volts peak to peak. As you see here on the lower right-hand side here. Right-hand side here. Lower left-hand side, I'm sorry. Now, let us now open the oscilloscope of the function generator of the COM3 Labs companion software, I'm sorry. Oscilloscope, let's open this. Make this display bigger. There. Easy to see. Now, what I'll do is this. Okay. Move this one a little down. See the setting. Here. Okay, now I'll switch on Y2 because I also have something connected on Y2. I'll click preview. Then I'll turn on the oscilloscope. There. Now, since the waveform is too wide, let me now change the horizontal time division setting. See here? Let me just change that one first. Horizontal time division. Let me put it at a higher value. Let's say 200 milliseconds first. See what this brings. There. Okay. Maybe a little bit more higher. 500 milliseconds, I think, would be fine. There, that's better. 500 milliseconds. Now, let me also adjust the Y1 square wave or the input square wave. Because right now, as you can see here, the Y1 square wave, which is the black square wave you see here, is actually overlapping its display on the Y2 square wave or the output. So that we can see the Y2 square wave, the output square wave, clearly. Let me just change the setting of the Y1 square wave, okay, so that it will display the square wave a little bit smaller than what we see here, or that the height will be a little bit smaller. To do that, I need to change the voltage setting here to make the height of the square wave smaller, make it smaller. I need to increase the voltage setting here, the volts per division setting here. Let's say from 2, let me set it to 5 volts. See what happens. There, okay, it's better. Now, what you see right here now, the black square wave here at the bottom is the input square wave, and the one there at the top, the blue one, is the output square wave. Now, let me just set the trigger to stop at Y1. And I'm going to put this one on one sweep. So it's easier to... There. Okay. Let us now try to analyze this output waveform. You see here on the right. Move the waveform on top so that you see it better. There. Now, interesting note here. As you can see here, when the input waveform is at the positive half cycle, the output is low. And when the input square wave is on the negative half cycle, the output is high. So what we have there is a reverse logic wherein at the positive half cycle of the square wave, the LED is off. And on the negative half cycle of the square wave, the LED is on, which is quite interesting. Now, remember that our input is an alternating square wave. It's not similar to the switch you saw earlier in the video wherein it's either on or off. This one is different. It has a positive half cycle and a negative half cycle. Although a negative voltage on the base or a negative current on the base will also reverse bias the base emitter junction, however, the effect on that on the collector is a little bit different compared to a straightforward on and off switch. I will not answer this question for now. I'll post this as a quiz to those who have watched this video. If you know the answer, just write it on the comment and I'll try to confirm it if your answer is correct or not once I have time to do so. With that, I would like to close the video for today. And as always, I'm encouraging everybody to keep experimenting, keep learning, and I hope to see you next time here in Derektronic.